was the same everywhere, so we solved for the voltage. Here the current is the same in each element, we solve for the current. So we start with the initial integral differential equation, differentiate the equation, we get the second order for the current. It looks similar except one thing. Alpha, the damping coefficient, is R over 2L. For parallel, it was 1 over 2 RC. For series is R over 2L. Otherwise, omega 0 is the same. And when you write the equation in using alpha and omega 0, it looks the same. Which is fine. Which is exactly what we want, because if you study this kind of equation, if you know how it behaves, then no matter what the system looks like, if it's a second order system, if it's a second order linear system, it will be described by that equation. Only alpha and omega 0 will be defined by particulars of the system. So in mechanical engineering, we study this equation, as well as anywhere when there is a second order system or higher order systems, that are linear. So that's why we always sort of try to convert everything to this form, and then we know exactly the solution. So we won't go again through particular solutions. What else do we have here? Okay, let's finish with the force response. Okay, because now we looked only at the natural response. You know that when you have stimulus connected to the system, and it's still the same linear, nicely behaved system, the total response will be the sum of two responses, of the force response and natural response. So we know how to find the natural response. You look at the initial conditions and note the source is disconnected or made zero, which of course means different things depending on the source. Remember, voltage source becomes a short circuit, current source becomes an open circuit. You look at, so you remove the source, you make zero all the sources, you find the natural response, and then you find the force response. And the force response depends, of course, on the type of the stimulus. If the stimulus is DC and you switch it on, then of course you know that force response is the response after the transient disappeared. The natural response disappears to zero, okay, because it always has this decaying, exponentially decaying terms. So when that goes to zero, at infinity, only the force response remains. And it's easy to calculate. It's a DC response, okay, for DC source. So for this one, for example, we know that the final current at the circuit, through the circuit will be zero, okay, and we know that the final voltage across the capacitor will be equal to Vs, because inductor will be a short circuit, the current will not flow, so resistor will have no voltage across it, so the final voltage appearing here will be equal to Vs. So you can find easily those forced values, which are essentially the values that are when t tends to infinity. If the source is happens to be sinusoidal or varying in some way, then of course the force response will also be varying in the same way. So if the source is sinusoidal, all the force responses in the circuit will be sinusoidal, and you know how to find them because we know how to analyze the circuit in frequency domain. Okay, so you can easily do that, and we'll go into that a little bit later on in a few more lectures from now. We'll look at some generalized source which will be exponentially decaying sinusoidal source, and we know that the response will also be exponentially decaying sinusoidal response. We can do some interesting things with this kind of sources. So finding the force response shouldn't be difficult. because it's either DC or it's sinusoidal. Okay? So we know how to do it, and then we combine these two, the force and the natural, and you get the total response. So, as I already mentioned here, you look at the force first, you find it, and then you do the natural. So when everything goes, that's what the force response would look like. Okay? So because this particular circuit was underdamped, it will be oscillating a little bit, but eventually it will settle to the force voltage, which was 1 volt. And you can, of course, analyze, because this function is standardized, you can analyze things like rise time, fall time, overshoot, and so on. And you can find it. For example, you can find the time of maximum, which is useful, and the value of the maximum. Okay, if you find the time, of course, you can find the value. So again, in lecture notes, there is a derivation, not very difficult. If you know your calculus. And I think that's all I wanted to do today.